This video is part 9 in a series of narrated long-form videos to sit alongside my A-level chemistry speedrun series, so that when you're going through the exam question you can see why I've done what I've done at each stage. Question 9 is taken from the rate equation topic, and I really like this topic because the questions are so very formulaic. There's really only one series of things they can ask you, and so once you've done one question and mastered that, you kind of have the whole topic nailed. So in this question, we're looking to calculate a value for K. And remember, this is this rate constant, which is going to make your rate equation numerically make sense. It's going to relate the rate of reaction to the concentration of the reactants. So in order to calculate K, firstly, we need a rate equation. And for that, we need to know what the order of reaction is with respect to each one of the reactants. So I'm going to look at this table of values and I'm looking for a pair of reactions where only one concentration has changed, because I can't draw any conclusions about the impact of concentration on rate if I'm changing two things at the same time. That's just the scientific method, isn't it? So if I look at this first pair of experiments, I can see that the concentration of A has tripled, whereas the concentration of B has not changed. And that's what I'm looking for, just one thing changing. Now, as you know, for A-level chemistry, there are only 3 possible options available to me. So as my concentration of A has tripled, has the rate not changed at all, in which case we would say it is 0th order with respect to reactant A. Has it also tripled? Because as we know, if something is first order, then if we double the concentration, the rate will double. If we triple the concentration, the rate will triple. If we quadruple the concentration, then the rate will quadruple. Or is the rate increasing by a factor of 9? Because if it's second order with respect to A, then we would expect that as we double the concentration, we quadruple the rate, and as we triple the concentration, we increase the rate by a factor of 9. So here it's the last option, and therefore the reaction is second order with respect to A. So far we can say that rate equals K multiplied by the concentration of A, using my square brackets, of course, for concentration, squared. And then I don't know what the term for B is going to be. So I look back at my table, and in an ideal world, I'd have another pair of reactions where just B is changing, but of course they never give us that. So now we're going to have to kind of make up an experiment to help us out here. So we know what happens with A, and therefore we can say, well, what would happen if A did its thing and if B was 0th order? Because if B was 0th order, then it wouldn't have any impact. So basically what we do is we create this hypothetical experiment where A, which we already know about, we already know it's second order, is going to change, but B is not going to change the concentration. And if it turns out that that is the same as something where we do change B, then we know it's 0th order, and we can kind of draw further conclusions from there. So in this fourth experiment, we're going to change A, but we're not going to change B. So if you look, I've changed the concentration of A to match the third experiment. So that's then doubled compared to experiment 2, but I've left the concentration of B the same as it was in experiment 2. And if that were the case, so I've doubled A, but I've kept B the same, then I would predict that the rate of reaction would quadruple, because we're second order with respect to A, and so that would give me a rate of that. So now I can compare this to my third experiment that I haven't actually used yet and figure out whether we're 0th first or second order with respect to B. So if what I just come up with was exactly the same as number 3, it would be 0th order, but it's not. So here I'm actually halving the concentration of B compared to my hypothetical experiment, and what has happened to the rate? Has it stayed the same? Has it also halved? Has it quartered? So in this instance, the rate has halved, and therefore we're first order with respect to B. So we can now write out that full rate equation like this. So now we can pick any line of the table. It doesn't matter which of the 4 lines you use, we'll get the same thing out. So we're just going to plug in values for rate and A and B and solve this. So we rearrange the equation and we get an answer of 3.5 times 10 to the minus 5. Thanks very much for watching, and if you are finding these videos useful, then don't forget to like and subscribe for more A-level chemistry content coming soon.